Good afternoon, everyone, and welcome to the next session of the MOFspace webinar series. Thank you for joining us today. We hope you will enjoy today's session. And as a short reminder, this webinar is an initiative within U4MOFs Cost Action. It's a European network bringing together experts and researchers working in the field of metal organic frameworks and other porous materials. Today's webinar is a special one because it marks the end of the first season of the MOFspace webinar series. And after a short break in August, we will come back in September with an updated format and new exciting topics. So as usually, the session is being recorded and will later be uploaded to our YouTube channel. By the way, if you miss any of our previous webinar, you can go to our YouTube channel and watch them there. Okay, so today we are very pleased to welcome Professor Valentina Colombo, Associate Professor of General and Inorganic Chemistry at the Department of Chemistry of the University of Milan, Italy. Professor Colombo is a highly recognized researcher in the field of solid-state chemistry, crystallography, and functional porous materials. Her research focuses on understanding how MOFs respond to external stimuli, interact with guest molecules, and evolve under working conditions. After completing her PhD at the University of Insubria, where she worked on pyrazolate-based MOFs, Professor Colombo continued her scientific career through several important international and national research experiences. These include research periods at the University of Granada and the University of California, Berkeley, as well as successive academic positions at the University of Milan, where she became associate professor in 2020. Since 2019, she has held the Functional Porous Materials Group at the Department of Chemistry of the University of Milan. Her group combines in situ and operando X-ray diffraction with spectroscopic techniques and theoretical modeling to investigate structure property relationships, framework flexibility, phase transition, adsorption mechanisms, active sites, and host gas interactions. Professor Colombo has authored more than 50 publications in high-impact journals. She has also received several important recognitions, including the 2024 Nardelli Prize from the Italian Association of Crystallography. In addition, Professor Colombo is the promoter and co-director of the MOF School, International School on Porous Materials. She is also a member of the International Scientific Committee of the EuroMOF Conference Series and will chair EuroMOF 2027. So today, Professor Colombo will discuss how in situ and operando crystallographic approaches allow us to move beyond static structure determination and understand how MOFs behave while they work. So we are very grateful to Professor Colombo for joining us today and sharing her expertise with the MOFspace community. So Valentina, please, the floor is yours.
Okay. Okay, thank you, Olesia, for this super nice introduction. Good afternoon, everyone. Of course, thank you very much, both of you, for the nice invitation. It is a great pleasure for me to contribute to the cost action initiatives, which I think are very, very important for our communities. And I'm also happy to be here to talk about our work on metal organic frameworks from a crystallographic perspective. So the title of this talk you see is Crystallography Beyond Structure in Metal Organic Frameworks. And the word I would like to emphasize in this title is beyond. This is because, of course, crystallography is essential to determine structure. But in this lecture, actually, I would like to show how crystallography can help us understand what a MOF does while it is working. So how it adsorbs molecules, how the framework responds, how disorder appear, and how structural information can be connected into function of our materials. So the main idea of this talk is that crystallography, of course, is not only a way to describe the material, it can also become a way to follow the function of our materials. Let me see. Okay, we tried everything before and now everything changed. So in MOFs, we know the most interesting part is the most interesting part of the structure actually is often what is not there. So it's the void. The void is not simply empty space in a metallic framework. It's the place where molecules enter, where they diffuse, react, and sometimes also trigger structure changes. So in MOF materials, emptiness function of the material begins. And while I was preparing the talk, I was thinking about the concept of porosity. Porosity is actually the design principle, and nature uses porosity everywhere, uses empty space everywhere to make material lighter, stronger, selective, but also responsive. And what MOF chemistry does allow us to do actually is to take this principle and translate it into crystalline materials, where the internal surface can be indeed designed with molecular precision. So in metal organic framework, porosity is not just the property that we measure after synthesis. It is actually part of the design strategy of our materials. So we choose building blocks, we create a certain architecture, and that architecture defines the space where function will take place. And this actually was the dream behind the reticular chemistry. So to build extended crystalline structure from molecular building blocks, the important conceptual shift was that porosity didn't have to be accidental. It was needed to be designed with the material itself. So empty space could become part of the design of the material by choosing the geometry, the connectivity of the building units. The chemist, our community, can start designing not only where atoms are, but also where atoms are not, so where empty space is. Of course, we have in our mind the definition of metal organic framework as crystalline materials built from metal nodes and organic linkers, which seems to be a very simple definition, but it has very, very deep consequences. The framework defines the permanent empty space. The pores, the channels, the cavities are not just leftover space between atoms. They are encoded in the architecture of the materials. So this is why MOF changed the way that chemists think about crystalline solids. So we can design the framework and the void together. The void becomes a chemical project. It can also molecules recognize them, respond, and sometimes also transform itself together with the molecules. So over the years, we became very good, extremely good. We as the community, let's say, at controlling porosity. So by changing metal nodes, the linker length, the topology, and maybe the degree of interpenetration, we learned how to tune the pore size, pore shape, and the internal surface area. So this led to a kind of race toward record-breaking surface area. So I think this is the updated one, but I might be also wrong. but sometimes, in some of the materials we have synthesized contains thousands of square meters of internal surface per gram. And in this story, somewhere in this story, there is also my first MOF. It was not exactly the world record material, but it was important, of course, for me because it was my entry point into this into the idea that empty space can be designed, measured, modified, but also structurally characterized. And of course, surface area is not always the final goal for our science. And actually, this is also a good memory of my PhD work, the front cover of my PhD thesis. A porous materials become functional when the framework is no longer alone. Okay, so when gases, vapor, solvents, reactants, whatever you want, enter into the pores, the relevant structure is not, or is often not, the empty framework measured under ambient conditions, if it is possible to have it. So the relevant structure may be the one under gas pressure, vapor, temperature, reaction conditions. And this is where actually adsorption, other properties like catalysis, structural response begin. So gas molecules interacts with the pore walls of the MOF. Reactants can be confined. Let me take this. Can be confined into near active sites. The framework may be breathed, distort, undergo phase transition, develop defects, and so on. So the question becomes, how do we observe the material while it is working? This is the point actually where crystallography becomes essential in this work. So we need structural tools that allow us to understand the material while it is functioning. Oop. Okay. So, and this is where diffraction enters into the story. If we don't know the structure, we can't rationalize the function. I always say this is something I've learned to say during MOF school lectures. So diffraction is one of the main ways in which we connect MOF, structure, and function. And of course, diffraction allows us to determine the framework architecture, the metal nodes, the linkers, the topology, the symmetry, and then the unit cell and all the crystallographic parameters. But the functional MOF, in functional MOFs, diffraction can do more than this. We all know that. It can help locate gas molecules inside the pore, can reveal framework responses such as breathing, gate opening, but also phase transitions. It can provide structural models that are essential for simulation, for examples. For DFT, for grand canonical Monte Carlo calculations. And when diffraction is also combined with complementary methods such as pair distribution function, total scattering experiments, X-ray absorption spectroscopy, infrared spectroscopy, and so on, it can also help us to approach disorder, defects, local environments, reactivity, and fine details of the structure. So in this talk, I will use crystallography not simply as a technique for structural determination, but as a way to connect the structure, porosity, and function of these materials. So there is, of course, a fundamental limitation if we use ex situ crystallography. Very often, I already said the same concept a few seconds ago. Very often, we measure only two states. For example, as synthesized materials still containing solvents and activated materials, so after solvent removal, or for example, empty framework and gas-loaded framework. So the two structures, of course, are very important in determine in rationalize the function of the materials. They tell us where the system starts and where it ends, but they don't tell us what happens in between. So, for example, does the framework change continuously or stepwise? Are intermediate phase formed? Does the material lose crystallinity and then recover it? Or are defects generated during activation, adsorption, and so on? So in metal organic frameworks, structural elucidation, the pathway can be as important as the final state. So function often happens between the two snapshots. And this is why we need to move from isolated ex situ structure to structures, what I say, I will call during this talk structural movies. So experiment that allows us to follow the material while an external condition change. Okay, so this brings me to the main example of this talk. So crystallography is often associated with the question, what is the structure? But for functional MOFs, we also want to ask, does the structure do? So if the experiment is carefully designed and the data are properly treated, crystallographic data can give us much more than a structural model. So they can tell us how many gas molecules are inside the pores, of course, where these molecules are located, how are the interaction between host and gas, the gas molecule and the framework, how the population changes with pressure, temperature, and how the framework itself responds. So in lucky, favorable cases, let's say this information can be even transformed into adsorption isotherms. This is what I will show you in a moment, and also help us in retrieving thermodynamic quantities. So in this first example, I will show how CO2 adsorption works in an iron pyrazolate-based framework, and how we used high resolution powder X-ray diffraction from the synchrotron to not only to observe the framework but also to quantify the adsorption from the structural point of view. Okay. So the material we choose is a good material for the purposes, the crystallographic purposes we had, because it combines three important features. It is crystalline, permanently porous, robust enough to remain ordered during activation and gas loading. We wanted to have a high crystalline material and a not flexible system. This was essential for the study I want to show you in a moment. So if the framework, of course, in this case, the question, as I said, was not only how iron BDP adsorbs CO2, but the question was of this experiment was actually more ambitious. Let's say can we follow CO2 adsorption inside the pores using diffraction, and then can we extract quantitative adsorption information, powder X-ray diffraction adsorption isotherms from the crystallographic data. Okay, iron BDP is known in the literature since 2013 from Jeff Long group. It is an orthorhombic system with these octahedral chains of iron 3 plus metal nodes with exobidentate pyrazolate linkers running along one direction. So the framework has these typical triangular channels running along one specific crystallographic direction. And takes a while to move from one slide to another one. Okay. So before performing the experiments, we of course, we verified that the material can be activated without collapse. And thermal analysis confirmed that gas removal can occur before framework decompositions. We did a variable temperature laboratory scale experiment to follow the behavior and to validate the high thermal stability of this material. The structural change, if you see this graph, is very small. This is the variation of the unit cell parameters while raising the temperature. And this is actually the biggest let's say, variation is directly related to the iron-iron separation along the one-dimensional iron pyrazolate chains. And this is actually strongly related to the rigid nature of this system. So even upon activation, the framework can slightly adjust, but it cannot deform dramatically. And this confirms a rigid nature of this system. So the materials also show CO2 capture behavior under dynamic condition. This has been done by our colleague and friends in Granada, Professor Jorge Navarro. And in the breakthrough experiment, a gas mixture has been passed through the bed of the adsorbent. The outlet gas was measured with time, and when CO2, of course, appears later at the outlet, this means that is retained more strongly than the rest of the gas mixture. It's just to explain this experiment quickly. So the breakthrough curves show that iron BDP is selective for CO2 under flow condition. It does have exceptional performance, but it has good performances for this type of MOF. But the breakthrough experiment does not tell us where the CO2 molecules are located inside the pores, how the adsorption sites are populated, or whether the frameworks respond in a specific way during the uptake. So, and this is where crystallography becomes useful. So I come back to the experiment. We move here from the macroscopic adsorption measured with breakthrough experiment and classical adsorption experiment to structural adsorption. We collected high resolution powder X-ray diffraction pattern at two different temperatures. Here is shown only the 298 K, but we collected also 273 K, while increasing the CO2 pressure from 0 to 8 bar. Each pattern corresponds to a defined pressure point, so the sequence of pattern can be seen as a structural movie for CO2 adsorption. And the important point is that the material remains crystalline through the experiment. The data quality is high enough for quantitative refinement at each pressure point. So peak position will tell us how the unit cell changes while CO2 is adsorbed inside the pores, and peak intensities will contain the information about electron density inside the pore, so therefore about the location and exact amount of CO2 inside the pore. And the diffraction pattern will not only be a fingerprint of the framework, but also become, with a proper data treatment, a source of quantitative information for gas uptake. Okay. So the case step is the data treatment that I said. For each CO2 pressure, we refine the structure. This means that at each pressure point is not only one point in an adsorption experiment, but is also one crystallographic model. Okay, if you compare porosimetry with crystallography experiment. So from the same diffraction data, we can extract the evolution of the unit cell, the structural response of the framework, the location of the CO2 adsorption site, and the occupancies of those sites. And the occupancy is particularly important because it tells us how populated a given adsorption site is at each pressure point. So by repeating this analysis for all pressure points, we can transform, let's say, the sequence of diffraction patterns into a pressure-dependent structural description of the adsorption process. So in other words, diffraction allow us to move from CO2 adsorbed to this is where CO2 is, and this is how the population changes during adsorption. So with this level of resolution at the synchrotron, we can also see very subtle details. We see that iron BDP is not completely rigid framework. Is in the activated material, you can see it in this picture. The framework shows a higher degree of rotational disorder. The linkers have more freedom when the pores are empty. As CO2 pressure increases, this disorder progressively decreases, suggesting that the adsorption sites are unworked inside the pores, and they have a sort of stabilizing effect on the framework. So we located three different adsorption sites during the data treatment, and it is interesting to see that the three CO2 adsorption sites are always on work at from 0 bar up to 8 bar, and this means that these sites are energetically very similar, and all three of them are indeed populated at each pressure point. So we are following now the framework, locating the gas and measuring also how the population of the adsorption site is. Okay. So once the CO2 adsorption site have been located, we can also look at the structure and see how they interact inside the pore. So the structural models show that CO2 is not simply somewhere disordered in the pores. We have three adsorption sites. The molecules interact with the pore walls through mostly side-on interaction, but they can also interact within each others into the pore channels, which is actually consistent with the one-dimensional nature of this MOF. So the next step that you see in this slide is actually a quantitative step. For each pressure point, we can sum the refined occupancies for the CO2 sites and convert them into the CO2 loading values. And in this way, we obtain what we call powder X-ray diffraction adsorption isotherms. So the adsorption curves built directly from the crystallographic refinements. These powder X-ray diffraction derived isotherm are can be treated as adsorption isotherms collected on the porosimeter. So we decided to apply the Langmuir-Freundlich model, which allowed us to describe the pressure-dependent CO2 uptake at different temperature. And this is actually exactly the step in which crystallography becomes a quantitative adsorption information. So once the powder X-ray diffraction adsorption isotherm are modeled at two different temperatures, we can also apply what is the Clausius-Clapeyron equation to determine the isosteric heat of adsorption. And this is actually the thermodynamic parameter. You can see it in orange in this graph. This is actually the thermodynamic parameter that can tell us how strongly the CO2 interacts with the framework as a function of loading. And the important point is that we can compare this value with the heat of adsorption, the QST, obtained from conventional volumetric adsorption measurements, for example, by using porosimetry. And of course, the two experiments are very different. The setup is different, the equilibration time, and blah, blah, blah. But the powder X-ray, so the volumetric measurement is bulk adsorption measurement. It gives the macroscopic uptake of the sample. The powder X-ray diffraction experiment instead gives adsorption information derived from structural refinements. So we would not expect that the two experiments to be identical in what they measure, but the agreement in QST is very good, and this is the key validation of this work. And these slides actually summarize the first message of this talk. What did crystallography add to the CO2 adsorption story? First, 3 points, let's say. So first, it shows that the structural response of the framework, even if it is considered a robust framework, is not a passive container, let's say. Okay, it can undergo subtle structural changes during adsorption, and with high resolution, we can see them and we can refine them. Second, it also allowed the gas occupancy to be quantified. So the refined CO2 sites becomes absorption data. And third, by combining measurement at different temperature with the proper data treatment, the adsorption data can be also connected to the thermodynamic information. So crystallography moves from structural determination to actually functional understanding beyond structural determination. So this is the first key message. If the experiment is carefully designed and the data are treated properly, So diffraction can become a quantitative probe of adsorption in working MOFs. So far, I've shown how crystallography can quantify CO2 adsorption in a robust framework. The example was clean. And I will move to a second example that is not fully understood. In our group, we are working on it, but the idea is, of course, and many approaches in MOF chemistry is to tune the pore chemistry, introducing functional groups into the pore walls. Actually, we wanted to see the differences from the crystallographic point of view by adding a tag into the pore walls of this iron BDP framework. And we prepared the series of iron BDP with amino functionalization on the linker. Actually, we are not completely changing the framework family. We are just progressively modifying the chemical environment inside the pore. Okay. So if you see the data, I am summarizing only the data of the parent iron BDP and the fully amino one. You will see that actually the surface area that is not actually reported, I see now, is lower compared to the iron BDP MOF. When the amino groups are introduced, this was actually expected, but at the same time, the amino groups improves the interaction with the CO2, which is a quadrupolar molecule, and the interaction with this type of group, even if are not aliphatic but aromatic, still play a good role. So as a result, the CO2 adsorption capacity has been improved. So we wanted to see, okay, the crystallographic model of this amino functionalized framework after activation. So this is 0 bar to 98K. The important point is how much my student Julia struggled for this refinement. She performed 2 times the synchrotron experiment because she had doubt on that, and we still have those. Once the amino group are introduced, the framework must be described as disordered structure. Okay, there are 3 main contributions actually to this disorder that comes out from the refinement. First is the rotational disorder of the organic linker we have seen already in the example of the bare iron BDP. This means that in the activated material, the linkers do not adopt a single wear-oriented orientation through the crystal, but they can rotate and have different orientation. Second, there is a positional disorder of the amino groups. The amino substituents are not all ordered into a unique crystallographic direction. Their position is statistically distributed, which reflects the local pore environment. And third, the refinement suggests also the presence of mislinker defects. This means that some linker position may not be fully occupied, generating vacancies or local interruptions in the framework connectivity. This is difficult to be refined from powder X-ray diffraction data. Structure is very important. So the amino group are introduced to improve the CO2 interaction, but they also make the pore environment less uniform. So the material is no longer an ideal periodic framework with identical pore everywhere. It is a real MOF with local heterogeneity, disorder, and possibly defect. Can we still extract quantitative information for a model complicated like this? In the previous example was a clean example, so everything worked well because the framework was rigid and simple. Here, instead, we have a more complex situation, rotational disorder, positional disorder, and possible missing linker defects. But we can start from the refined structural model and use the adsorption isotherms to collect with CO2 physisorbate CO2 molecules and refine the occupancy. So even if the framework is very disordered, we can also retrieve some good information that needs to be validated in this case. So the model here needs to be treated with more caution because the pore environment is less uniform, the refinement is more delicate, and this is actually the point in which we see the limit of average crystallography. From ritual refinement, we know that the amino-functionalized framework cannot be described as a perfectly ordered structure. But powder diffraction, mainly gives us an average structure, tell us how the framework looks on average over many unit cells. So for the material that contains local heterogeneity, different iron environments, defects, these may not be fully resolved by average crystallography. So this is why we started to explore complementary local probe, in particular X-ray absorption spectroscopy, carbon monoxide chemisorption, in situ infrared experiment to validate our structural model with external, let's say, local probe that can confirm us the presence of structural defects. Okay, so for the example, I've shown and relied on high-resolution crystallosynchrotron powder diffraction experiment. These are very powerful because they gave you high-quality data, but of course, synchrotron access can be limited. Not every adsorption question can be studied only at beam time, only on the beam line. So the next question is, can we bring this way of thinking into the laboratory? So can we design experiment where controlled gas or vapor dosing is combined with laboratory powder X-ray diffraction or single crystal X-ray diffraction, so we can follow adsorption structurally even without the synchrotron radiation? Of course, the goal is not to reach the same level of high resolution and as synchrotron experiment, but good structural information are still information, even if taken from the laboratory sources, I mean. So many groups has worked in crystallography showing different setups for this type of experiment in laboratory scale. We have also our setups. I will not spend too much details into this, and I will just show you brief examples. So this is a quick example of what we can be done with a preparation in laboratory scale on a metal organic framework. This was a work published in 2020 with Jeff Long Group on a MOF containing vanadium-2 sites. So the materials is interesting because it can adsorb nitrogen through a very unusual mechanism of porous materials, the pi back bonding interaction between nitrogen, dinitrogen molecules and the vanadium-2 metal center. So in this case, we used the sealed capillaries. We prepared the hermetome. We refined some data at home. We reached a good level of confidence on the model, and then we moved to the synchrotron to have high resolution data to validate it. And in the activate structure, 60% of the vanadium sites are free and are vanadium-2 sites, while 40% of the sites still have a chlorine atom bonded to the vanadium site, as it's very difficult to obtain this material fully in its fully reduced way. So in this example, the structural information is essential because the selectivity of the MOF is not simply controlled by the pore size or the surface area, but is controlled by the local chemistry of the open metal sites and from the electronic interaction with the gas molecules. So we were able to characterize these nitrogen end-on coordination mode on the vanadium site. Other example is a second example that we still have to publish. In this case, the question was different. This was done in laboratory scale on single crystal. We were studying a flexible pillared MOF for CO2 capture, and it became clear that we had only a limited understanding on how the materials behave when CO2 is captured in the presence of moisture. This is an important point for applications for metal organic frameworks applications because water is often present as contaminant in real gas streams and can dramatically change the adsorption behavior of a material. So we studied in detail the crystal structure, inspected it carefully, and we were trying to find a structural explanation. The interesting observation actually in this case was that is shown here. In the S-synthesized water-loaded structure, the MOF is not completely filled. This is still about 60% of empty volume in the unit cell in the S-synthesized form of the material. So the residual voids are located close to the trapped water molecule that comes out from the synthesis, and they form a kind of continuous channel through the structure. So at this point, the question became, are these voids accessible? So can CO2 enter even when water is already present? And with laboratory scale crystallography, actually, we were able to characterize exactly this mechanism. So using in situ laboratory single crystal setup, we could follow this process directly and characterize co-adsorption of CO2 and water inside the framework. So the message is again the same. Crystallography allows us to transform an adsorption question to a structural question. It does not tell us only where CO2 is, when CO2 is captured in the presence of water. It helps us to understand the full process. Okay, I had an additional animation. So after this example, I will go through my last example, and I will like to move one step further. So far, I have shown that laboratory compatible crystallographic setup can be used to characterize gas loaded structure and to ask for specific structural question about adsorption. But the question is, can we also use laboratory powder X-ray diffraction in a more quantitative way? So in other words, can we build a powder X-ray diffraction adsorption isotherm from powder data collected in the laboratory? And the idea is conceptually actually similar to what I showed for the synchrotron experiment. So we dose gas or vapor in a controlled way, collect a diffraction pattern at each dosing point, and the structural parameter that changes with adsorption. So by plotting the crystallographic observable as a function of vapor or gas pressure and comparing it with the conventional volumetric isotherms, we can actually build the structural adsorption isotherm at laboratory scale and compare the bulk behavior with the atomic level of adsorption. So we choose this experiment. I come back in a second. We choose a ZIF8 as a model material, and this has been done in collaboration with the Rob Amelot group in KU Leuven, that I thank very much for the experimental support. So to test this approach, I said that we used the ZIF8 material, one of the most studied MOF, robust, chemically stable, well-known sodalite type structure with these cages connected through very narrow aperture. It is a very useful model system to study how small vapor molecules enter and move through the porous framework. In this case, we focused on methanol vapor adsorption. So the idea is simple. We activated the ZIF8 sample. We dose the methanol vapor in a controlled way while collecting powder X-ray diffraction data at the laboratory. And the question was exactly the same as before. And I will show you the experiment in the next slides as a movie. So we follow the methanol dosing step by step, and we look at how the unit cell respond and the structure respond along the adsorption isotherm. So the first structural parameter we follow is the unit cell parameter of ZIF8. It's a cubic MOF, so the A cell parameter during methanol vapor dosing. This is very simple observable, but very informative. It tells us how the framework respond globally when methanol enters in the pore. So at this stage, we will not discuss detailed structural model of the gas molecule, but we ask a more let's say, basic question. Does the framework expand, contract, or remain unchanged during methanol adsorption? So on this slide, we see the unit cell variation. And as methanol is dosed, the cell parameter does not change monotonically. This is very important. We observe a small contraction in this point of the cell at a specific relative humidity of methanol, followed by re-expansion of methanol during of the cell, sorry, during methanol loading increases. So keep this point in mind. This has been called in the literature a clustering point because this small contraction marks the beginning of different adsorption regime. And now we can compare the evolution of the unit cell parameter with the volumetric methanol adsorption data collected on the very same material. The comparison is very useful because it tells us where the structural response occurs along the adsorption process. Okay, and the key feature is exactly here, the clustering point. Around this region, the methanol molecules are no longer behaving simply as isolated gas entering independent in the adsorption site, but they began interact with each other, and structurally the MOF contract a bit to lower the energy of the system. So we start from the activated structure. This is the volumetric isotherm, and the point is the point corresponding to the Rietveld refinement. And this is actually the MOF activated before methanol adsorption, methanol dosing. This is the reference state, empty Z-phase structure against which we will compare the following step. So at low pressure, you see the small point changed. The first methanol molecules enter in the system, the uptake begins, and the diffraction data start to carry the information about the gas molecule and their interaction with the framework. Here we have only one crystallographic independent molecule on work. And then second, where the adsorption isotherm has a high steepness, the isotherm rises, let's say, more sharply, is where adsorption process becomes structurally very interesting. We are not anymore adding isolated molecules, but a second crystallographic independent methanol molecules enter into the pores, and there is a clustering of the methanol molecules inside the pore of the Z-phase. Then at the end, high vapor pressure, the system reaches a plateau. So the framework is now in the methanol load state, and the number of methanol molecules, crystallographically independent methanol molecules is the same, but the occupancy rises a bit. So this is the final state of the framework at the end of the experiment. And we can see this as a like adsorption movie. So this is the comparison of the powder X-ray diffraction isotherm collected in the laboratory with the volumetric methanol isotherm. So this does not replace high-resolution synchrotron experiment, of course, but it opens a practical route to study adsorption processes under accessible laboratory conditions. So not only powder diffraction used for phase purity and comparison, but becomes a way to follow function beyond the classical structural characterization. So the broader goal of this work is to extend this approach to different box and connect adsorption with diffusion and sensing. For second sensing, the equilibrium uptake is not enough. So a sensor response depends on not only on how much the analyte enters into the pore, but also on how fast they enter, how it diffuse through the framework. And we are combining now in collaboration with the Rob Amelot group, the powder X-ray adsorption isotherm with the diffusivity data to reply to a bigger question. So regarding the sensor response. Okay, so these examples are just to conclude my talk, part of a broader effort in our group. We will use diffraction, which is our primary expertise, and complementary spectroscopy with other colleagues expert in this field to understand the real functional MOFs, so the effective sites, surfaces, water harvesting, oxidation catalysis, and so on. So I will not discuss the examples today, but it's just as a way to thank the collaborators and the students working on other work that I couldn't present today. And so let me finish with some advertisement. So we will have the next edition of MOF School 2027 at the same location, Villa del Grumello on Lake Como. This will be held from 29th June, 3rd July 2027. And just after the school, the students will have the opportunity to come to EuroMOF 2027 from 4th to 7th July. Of course, there will also be the opportunity of the Young Investigator Symposium that we will organize for young researcher, and this is important for the audience of these seminars. And let me thank the committee because Italy is doing a big job behind this conference. And let me show you the beauty of the conference venue, which is a very, very unique place on Lake Como. So let me thank again my group members. Some of them are left, already left the group. And so now the group is not as big as in this picture. We will take another one. We'll rise again in the next semester. And let me also thank my family, always taking me busy, and all my collaborators and fundings. And you, of course, for listening to this long talk.
Thank you, Valentina. It was actually very interesting and useful talk. So now we have time for questions and discussion. I invite everyone to write your question in the chat or maybe simply raise your hand. Yes, and we will be happy to discuss them with Valentina. So please. Yes, Anna.
Thank you very much, Valentina, for a very inspiring talk and techniques to understand how MOFs behave. I have a couple of questions. First, about this clustering of methanol in CF8. Can you also understand which non-covalent interactions govern this clustering? Is it hydrogen bonding only between methanol molecules or also with the linkers? Can you see
yes.
it
So
from all the research
we of
data?
course have done a more detailed. We have done a more detailed observation on the crystallographic results of this Z8 methanol adsorption, and we were able to. I don't have additional slide, but we were able to study the rotation of the imidazole linkers because it has a rotation on the bonding between the two zinc ions. And also the interaction within methanol molecules and from methanol molecule with the framework. Actually, in the clustering point, the shortest interaction is gas-gas interaction. So from one methanol molecule to the other methanol molecules. And this is actually the clustering point when the first methanol enters and becomes more populated, the unit cell shrinks, and the main interaction is a gas-gas interaction. Then when the isotherm raises more sharply, the number of methanol molecules increases because we have two methanol molecules, two different adsorption sites. And in that case, the rotation of the imidazole linkers starts entering into the mechanism and the cell expands again.
Very nice. I'm very surprised that everything can be seen from powder XRD data. It's really impressive that you can refine all these details. And one more question about another example of this iron MOF, where you have different linkers, mixed linkers with the NH2 group or without. Have you tried to model the lower symmetry, to use lower symmetry model to refine this powder XRD data, and how did it go? Which properties did you have?
Yes, we didn't obtain anything that is significantly different from the higher symmetry model. So we discarded the option of lowering the symmetry to try to force the model being, ordered in some way, because actually with the double of parameters, the refinement was slightly better, but didn't have any, let's say, we couldn't believe it from the refinement. That's why on that system it is really needed another external probe to confirm the evidence we have on the powder X-ray diffraction refinements. Actually, we were suspecting a not complete activation of the MOF. That's why we repeated the synchrotron experiment, which means another proposal, blah, blah, blah. And we obtained exactly the same isotherm. So that's why we started thinking about possible defectivity of the MOF. And actually the refinements turns out very, very well with including the defect, the presence of linkers defects.
Okay, thank you very much.
I don't have a final reply on that.
No, it's amazing. Thank you.
Okay, thank you. We have one more question from Irina, please.
Hello. First, thank you very much for the very interesting report. I have two questions. First question is, have you ever had a situation where you couldn't retrieve structure from multiple refinements? Because I'm going in the same structure refinement, but as I know, you should have pretty good data and pretty good structural data for this. And probably if the MOF changes or structure changes dramatically, or disorder is very high, that could be. So have you ever had the situation, or you could do always the refinements just fine?
I'm not sure I've got the question well, because I can't hear you very well, but so you asked if it happens sometimes that we couldn't refine the data.
Yes, that you couldn't retrieve the structure from it.
Yeah, of course. Of course, yes. It depends on many factors. So ab initio structural solution from powder diffraction has some limits. And it strongly depends on how complicated the structure is, how good the data, the experimental data are, and so on and so forth. So, of course, it happens that we cannot refine the structural data from powder diffraction, but there are fortunately other techniques that can help in building a model. For example, nowadays there is electron diffraction that can help us in retrieving a model, for example, of an activated structure, and this can be used as a starting model for a refinement from powder diffraction data. We can use, of course, a single crystal X-ray diffraction to build a starting model that can then be used for powder X-ray diffraction refinements. So if directly from powder X-ray diffraction is difficult to retrieve ab initio the structure, there are ways to, face the problem and still work on the system with powder X-ray diffraction analysis.
Yes, sure. Thank you for the answer. And my second question is, have you studied how long do you MOF hold adsorbed gas. For example, the first example with CO2 absorption, if you just put off the pressure, how long does it take for the MOF to release all the CO2? And does it depend on chemical modifications?
I didn't get the question, I'm sorry. So if someone can help me, so
Irina, can you
because
type
I
it?
cannot hear well.
Can you type it in the chat, Irina?
Unfortunately, no. Somehow my chat doesn't work.
No,
I'll
the
try
chat should be open. See if
Yes,
you can try
just
that more.
it doesn't work on my phone, unfortunately. I
Ah,
don't know why.
okay. Okay.
I'll try to make louder. How long does it take for your MOF to release all the gas after you put off the pressure? And does it depend on the chemical modifications of MOF?
You mean the iron system?
Yes.
Okay. Yeah, I don't remember the time for the breakthrough experiments by my mind, but of course the release of CO2 in this system is not very slow because there are no strong chemical, let's say, chemical interactions. And the MOF for the bare iron BDP system works as a physisorbent. So the release of CO2 is actually very easy to reach with applying only vacuum to the system. For the amino groups is a bit different. But even in that case, we are not in a regime in which we can the CO2 forms carbamate with the amino groups. So there is a stronger interaction within the pore walls, but there is no chemisorption going on. So the desorption is still a let's say simple process.
Okay, yes, I understand. Thank you very much.
Thank you. And Evelyn has a question, please.
I have a brief one. I was actually wondering, what is the time resolution that you can go fastest? Because it's basically a snapshot, you get a crystal, so basically a structural information, next one. So how fast can you probe?
So we equilibrate the system
okay.
and we collect data through equilibration because if not, the comparison with the volumetric adsorption experiment will be not
okay. So static
not feasible. So of course, the synchrotron you can go faster with data collection. But in any case, with those the gas of the vapor, we wait at least 20 minutes. But it depends on the system, and then we collect the data set.
Okay.
Yes. So it's not time resolved crystallography in the term of very short time.
No, I mean this is
like minutes.
It's absolutely exciting technology because you know exactly where are the gas sites inside of the MOF that are happening with pressure, with time, with whatever you have. Spontaneously asked, are there any limitations that this technique can do? So any MOFs, be it copper or zirconium or any metal or any linker or anything that you can't use it for?
With this approach, it depends on so many factors from the quality of the diffraction of the system. This is first. If you are the synchrotron, okay, the peak profile is a lot better, and it's easier also to work on difficult samples. From laboratory scale, the line profile can be very difficult to model. And so, for example, the system we measured with Rob Amelot, so ZIF8 seems to be a simple system, but actually it's super difficult to work with in the laboratory. The profile shape is always very asymmetric. So my student Lorenzo, he worked a lot on the synthesis of the material to have a perfectly homogeneous size, samples in size. to try to lower, as much as possible this asymmetry of the peaks.
Okay.
And then, of course, as much higher the symmetry, as less parameter you have. So
True.
this can help a lot. It depends. It depends on.
Okay. But the take-home message for the students is try to make your MOF as
Don't use powder diffraction just to compare your pattern with the simulated one.
that is a perfect take-home message for today.
It's an easy take-home message, but it's very important.
Excellent.
Yes.
Okay, thank you. More questions, maybe?
Any questions that you ever wanted to ask an absolute expert on porous material?
Mhm. I don't see raised hands or questions in the chat. Okay, so thank you very much once again, Valentina, for your wonderful talk and for the very interesting discussion. Many thanks also to all participants for joining us today and for your questions. As mentioned at the beginning, this webinar concludes the first season of the MOFspace webinar series, and we will now take a short summer break and come back to you in September. So thank you all. Have a nice day and enjoy the summer.
Bye.
Thank you.
Thank you. Thank you for the
Bye.
invitation.